Frames of references are something that affect our lives daily. For example, when you're driving in a car. If you look at this apparatus here, you can see that there are two cars. And when these two cars are traveling towards each other at the same speed, it is evident that they're traveling towards each other at the same speed from this frame of reference. However, if you take the frame of reference and you're following just one of these cars, it appears as if this car is traveling not at all. It appears as if the rest of the world is traveling backwards, as well as this car is just part of the rest of the world traveling backwards as it stays stationary. If you look at the frame of reference from on top of this car, it appears as if this car over here is traveling at a constant speed that's twice as fast as it's actually traveling, because this car here is also traveling at a constant speed towards it.
Cars on my right doesn't look like they're going really fast because we're traveling around the same speed but in the same direction. But cars on my left look like they're going towards the speed because we're going opposite directions but same speed.
Okay, so now we're going to take a look at the more mathematical aspect of the physics cards. So if we have two physics cards facing each other, we are assuming there's no friction, so they're both moving at each other at constant velocity. This one with velocity, whatever that velocity is, and this one is moving towards the other way with negative velocity. Okay, so they're both moving towards each other with constant speed, but with opposite velocity vectors. Okay, so from the world frame of reference, this is obviously what's going on. But if we take those velocities and we go from the frame of reference of just this cart, it looks like this cart is stationary, and the world is moving towards it this way with negative velocity, and this cart is also moving towards it this way with also negative velocity. So if we add those two velocity vectors together, we get it's moving this way at negative 2v. So it looks like it's moving towards it twice as fast. And from the frame of reference of this card, you can't tell what's actually going on. So that's actually the math. Thank you.
In this video, we will be investigating the motion of objects in the Earth frame of reference versus the motion of objects in other frames of reference. If I drop an object, the object accelerates straight down, according to the Earth frame of reference, along the vertical reference line. When the ball is dropped from a moving car, the ball falls in a parabolic path according to the Earth frame of reference, which is a non-moving frame of reference. We are going to do this experiment again, but this time we will not be using the Earth frame of reference. We will be using a frame of reference that is fixed to the moving car. In this moving frame of reference, the ball falls straight down along the vertical reference line. Remember, this also occurred when neither the rock dropper nor the frame of reference was in motion. Each scenario looked exactly the same. In fact, if the background of the scenario in which both the car and the frame of reference were in motion was removed, it would be impossible to tell whether either was in motion. This observation is defined by Galilean Relativity, which states that absolute linear motion at a constant velocity cannot be detected, nor can absolute rest. All constant velocity frames of reference are equivalent. The laws of motion are the same in all inertial frames of reference. We can apply Galilean relativity to the second scenario, in which the car was moving with a constant velocity with respect to the non-moving frame of reference. However, the same laws of physics as in the other examples were still in use, that is to say, Newton's first and second laws. In fact, if the camera had been in the car and the ball thrown outside, the motion of the ball would appear in the same way, to take on a parabolic path. Galilean relativity states that the laws of motion are the same in all inertial frames. If the magnitude of the car's forward velocity matches or is equal to the magnitude of the ball's thrown backwards velocity, the ball will fall straight down along the vertical reference line. This occurs because the forward and backward velocity vectors will cancel each other out, resulting in a horizontal velocity equal to 0. With no horizontal velocity, the ball will be affected solely by gravity and will thus accelerate downwards at 9.81 meters per second squared. Thanks for investigating frames of reference with us. Physics is fun!
Hello and welcome to today's lesson on the frame of reference. My name is James Bell.
My name is Sarah. And my name is Lello. And today, it is our job to teach you what a frame of reference is. First off, let's go through what a frame of reference is.
A frame of reference is how you perceive the environment around you.
Exactly, like how you perceive this table to be still, when in fact it is spinning around the sun. This is because of your frame of reference.
Or to put it more simply, because you're spinning around the sun with the same rate as the table, it looks like nothing's happening at all.
Think of it this way. If we're pushing against each other with equal forces, from your point of view, nothing's happening.
Although from my point of view, I am pushing on Sarah here, and she's pushing back. Just because you don't see the forces doesn't mean they aren't happening.
Here's a better example. See if you can spot the difference between these two shots. Here's a hint. Watch the ball's trajectory. Did you catch it? Probably not, but we can assure you that these are two different videos with two different frames of reference. Here, we'll take you out of the frame of reference so you can spot the difference now.
A change in your frame of reference changes the problem. See how the ball's trajectory changed from a straight up and down line to a parabola?
This is because, like with the table, you were in the same frame of reference as the cart, which made the whole situation appear completely different.
Thanks for watching!
In the following video demonstration, we used a whiteboard with grid lines attached to low-friction carts, as well as a low-friction hover puck, to demonstrate Galilean relativity for Newton's first law of motion. For our first case, we applied no unbalanced force to either the whiteboard, the puck, or the camera, thus they all remained at rest relative to each other. In the second case, we applied a force to the puck. This made it so that the puck is in motion relative to the whiteboard and the camera, while the whiteboard and camera are in motion relative to the puck, and the whiteboard and camera are at rest relative to each other. For the third case, we applied a force to the whiteboard. This caused the whiteboard to be in motion relative to the puck and the camera, while the puck and camera were in motion relative to the whiteboard. This results in it being sometimes difficult to tell whether it's the whiteboard or the puck and camera in motion relative to the Earth. Finally, in our fourth case, we applied an equal force to both the whiteboard and the puck. This resulted in the whiteboard and puck being in motion relative to the camera, yet being at rest relative to each other.
Hello! I am Professor
teacher Jillian, and this is my colleague, Professor Wahaj.
And we are here discussing our thoughts about physics.
Specifically, frames of reference.
Wait a minute. Why are we in black and white? This is 2015. That's better. So, knowing us physicists, we like to experiment about our thoughts and ideas.
So why don't we go to the mall?
As you wish.
Wahaj,
What?
we're in a mall,
Yes.
and there are escalators here.
Yes.
Are you thinking what I'm thinking?
That we should explore different frames of reference and prove that Newton's laws apply to all inertial frames of reference?
I was thinking of going shopping, but that works too.
Alright then, I'll go on the escalator and we'll try to describe the motion from different frames of reference.
Okay, let's go. From my point of view, on the ground, the people on the escalator are moving at a constant velocity.
And from the frame of reference from the escalator, I'm standing still.
From different frames of reference, the motion can be described differently.
To illustrate this, I will be going up the escalator while Jillian goes up the stairs.
From Wahaj's point of view, if I'm walking faster up the stairs, I move forwards. If I'm slower, then I move backwards. And if I'm walking at the same speed, I don't move from his frame of reference.
But to an observer on the ground, we are both moving up.
So now that we've shown the different inertial frames of reference,
That is, frames of reference that are at rest, like the ground, or at a constant velocity, like the escalator,
now we will prove that Newton's first and second laws are valid in all inertial frames of reference.
to confirm this, Wahaj will hold a ball steady while going up the escalator.
While I'm holding the ball steady, like here, there are no net forces acting upon the ball.
From my frame of reference, the ball isn't moving.
And from my frame of reference on the ground, the ball is moving at a constant velocity. Therefore, Newton's first law is evident in this situation, from both inertial frames of reference.
According to Newton's second law, if a net force is applied to an object, it will accelerate. Watch as the force of gravity acts upon the ball.
From the ground, the ball is clearly accelerating due to gravity.
And from the escalator, this is evident as well.
What thrilling results! What a remarkable find!
I agree completely, Professor Wahaj. Newton's first and second laws are entirely legitimate in all inertial frames of reference.
And now we can just head back to the lab and continue to work on the results.
And I'm gonna go shopping.
See you later, folks.
Hey there, Isaac.
Hey, Albie.
I think you're upside down, man.
No, you're upside down.
There's no way I'm upside down. Like, no.
Yeah, Isn't you're upside down.
She creeping me out.
No, you're upside down. You're upside
no.
down.
No, you're upside down. What is this? Why are you always tricking me like that?
Yeah, no.
Isaac, stop, please. Stop.
Hey, what'd I tell you?
The movement of this water bottle is sort of similar to movement of things like elevators that we've seen in class. Now, the water inside the bottle and the bottle itself are being moved upward by the force of Mano's hand. Now, as this force is lessened, the water bottle stops moving so quickly, but the water inside still feels the fictitious upward force as the water bottle feels a downward acceleration. This is what makes the water go upwards as it reaches its peak. This example is more similar to a car. Now, the skateboard slowly accelerates forward, and as it quickly accelerates in the backwards direction, the water bottle feels a fictitious forward force and falls off. Now, this video has been significantly slowed down for us to truly appreciate the forces at play. As the water bottle accelerates in the right direction, the water bunches up at the left side because it feels an opposite fictitious force going towards the left. And similarly, when the water bottle goes to the left, the water goes to the right because it feels a rightward fictitious force.